0 to what? I think I heard it. R. 0 to R. So if it was the unit circle, yes, it would be 1, but we're doing an arbitrary radius. Okay? That's why this is important in the problem. Okay, do y'all understand? I can draw that curve, that blue curve, as long as I do this function on that interval. So why don't I find the arc length of that function then? And wouldn't that give me the length of that little quarter circle? And then I multiply times 4, and that would give me the length of the whole thing. Yeah? All right, so what are we going to need to do this if I'm going to find the length of that blue curve? What am I going to need? I'm going to need the derivative, and I'm going to need to square it. And that's going to look scary at first, but it's actually not going to be bad. So the derivative of this function is 1 over 2 roots of r squared minus x squared. Because the derivative of the square root of anything is 1 over 2 times the square root of that stuff inside. Then, derivative of what's in here. And what's the derivative of what's in there? Remember, r is a constant. Right? R is a fixed number here. So what's the derivative of a constant? 0, and then derivative of negative x squared is negative 2x. Yeah? That's times right there. And the 2's cancel, and I still have a negative x on top, and on the bottom I have square root r squared minus x squared, like that. That's f prime. Square it. It looks like things are getting ugly, right? Like, this is somewhat intimidating looking at this. But when you square the bottom, the square root goes away, so that does make us feel better, right? So x squared here, not quite. 2 terms can't do it that way. All right, so that's our derivative squared. Let's go to the formula. Arc length is integral, right? Blah, 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 square root 1 plus that thing. So my arc length of that blue piece should be the integral from 0 to the constant r, square root 1 plus x squared over r squared minus x squared dx. That looks pretty bad, but we just learned a lesson in the last problem that when we see complicated integrals like that with roots like this, that one thing that kind of saves the day sometimes is to combine. Common denominator. Put these two together, right? So what must you put here and here? R squared minus x squared, top and bottom. I'm going to go ahead and just throw it in here. R squared minus x squared, R squared minus x squared. That's 1, right? Put the two together, and what happens? Your x squareds cancel. You're just left with an r squared up there, aren't you? Okay, I'm going to have to continue. Clear myself some room here. So the length is equal to integral 0 to r square root, what do you say was left on top? R squared, and on the bottom, r squared minus x squared. Still looking pretty bad, but r is a constant. So let's do the root of the top and bottom separately right now. What's the root of the top? R, right? And r is a constant. Bring it out of the integral. I will have a 1 up here, and then on the bottom I still have a square root of r squared minus x squared dx. So do y'all see what happened with the r? Take the root of it, you get r, pop it out, because it doesn't have an x attached to it. Now this root thing on the bottom I can't pop out because it's got an x in there. Could do trig sub, but I can do even better because that's a direct formula. Arc sine. Remember, tangent is squared, squared, added together, no root. So this one is arc sine. I believe it's formula 16. So the antiderivative of this, remember we have the r out front, the antiderivative of this should be sine inverse of, the formula in your sheet is u over a. In this case, u is really the variable x, so we have x over, and we don't have a here, we're using r. So if you don't have any idea where that came from, I suggest you look at your formula sheet and make sure you can come up with that. This line is going to be integrated from 0 to r, right? We're pretty much there now. First plug in r. R for x. R divided by r? 1. Arc sine of 1. That's asking you at what angle is sine 1? Pi over 2. Okay? So when we plug in r, we get r times pi over 2, right? Minus, then when we plug in 0, 0 over r is 0. Arc sine of 0 is 0. So that zeroes out. So our answer is basically 1/2 pi r. That's the answer. So are we right? Yeah, that was, remember, that was only 1/4 of the circumference. So multiply that by 4, and what do you get? 2 pi. Confetti? No? So we've proven that the circumference of a circle is 2 pi r. All right, good. We've got about 15 minutes. Y'all good? Y'all feeling good? 7.5, surface area. I had a student tell me the other day, it wasn't a student from this class, it was just another, I'll leave them anonymous. They were getting upset with me about how much material I was making them have to learn in this class. And I said, take it to the state of Texas. Don't tell me. State of Texas determines what Cal 2 is. And even at this pace, we're not going to finish the whole course. There's no way we'll make it. So, you know, what's that? We won't get through, we probably won't get to polar coordinates and polar equations. We probably won't. If so, it'll just be like a one-day type thing. But not to worry, because polar coordinates and parametric equations is something that you can pick up very quickly. It's not like techniques of integration where we have to spend several weeks on it because you have to do a bunch of repetition. It's something that you can just okay, yeah, there it is, I get it, no big deal, move on. It really is easier to swallow later. So trust me, I wouldn't leave you hang out to dry like that, leave a whole part of this class out. Some things you can put Band-Aids on, right? Yeah. And other things you can't. Polar coordinates is one of those things you can put a Band-Aid on it later. Sequences and series, you can't put a Band-Aid on that. You have to spend time on it. So, all right, surface area. Let's go back. Almost the same problem we just had. You've got this curve sitting here. We just found a way to measure its length. Now what I'm going to do is I'm going to wrap it around the x-axis again. But this time, I'm not wrapping a region around. Remember, when we were wrapping before, we were wrapping an entire region around, and that region was creating a solid, wasn't it? This time, if I just wrap just this curve around, it's going to create this weird shaped, almost like a, I don't know. It's almost like a bell that's kind of been turned sideways and cut the top off. Doesn't that kind of look like a bell? It's hollow, right? I could put my hand in here and it's hollow, except it has this shell shape to it, right? And the question is, what's the surface area? So if I wanted to actually come in here and paint the outside of this, what would the area of that outside be?
So instead of washers, it's the Arclength added up.
Yeah, instead of washers, it's like an Arclength added up. Very good. But let's see, there's a little bit in there we have to be careful with. So let's go back over here. Let's do an infinitesimal cut. All right, and let's take just this right here and just wrap that little segment around. If we wrap just that little segment around, it would have given us like one little strip of this, wouldn't it have? One little strip? Let's look at that over here, though, without the whole picture. It would just look like one little strip, like this. And it would be hollow. This looks almost like a rubber band, right? Like if I had a rubber band sitting out here. And I want its area. So I'm going to come in here and I'm going to cut it with a pair of scissors. Cut it, and I'm going to lay it out flat. And when I lay it out flat, I get this long, narrow strip, which is a rectangle. And what is the area of that rectangle? That's the question, right? What's the area of this? I'll start with the easier part. What is this length? 2 pi r. But r is actually the distance from here to here, right? Which, if we come back, is actually the distance from here to here. So if this is the function f of x, isn't the radius just f of x? Right? This distance is the same as this distance, and that's f of x. Do you all understand why it's 2 pi times f of x? That picture that we had earlier, where if this goes like this, and I cut it and open it up, then this length was the circumference, wasn't it? So 2 pi times the radius, but the radius is the function's height. That all, I think that's okay, yeah? The width is the part that is tricky. Because your instinct really probably wants to tell you dx. But it's not dx. Dx is the width of this, right? But the width of our rubber band is actually has a slight angle to it, doesn't it? It's actually the length of that little arc piece, right? Because this may be curved here, and so there's actually maybe a little bit of a curvature to the top of that. So we need to account for that. So that little slice right there, this little piece, is actually the arc length. And the formula for the arc length, we just derived it. It was this: 1 plus the function's derivative squared dx. Okay, so it's the circumference of the rubber band times the width of it, but the width of it is the arc length of the rubber band, or the arc length of that little strip. So in terms of a formula, right, with integrals and stuff, is this not going to look a lot like the arc length formula? Don't you think it will? Let's see. See what our formula should look like. You tell me. Maybe you can come up with it. Surface area should be integral. Where to where? I didn't label it on my graph, but a to b, because it's my x, right? So a to b. 2 pi, right? 2 pi is going to pop out because 2 pi is a constant, right? And then we have f of x. That can't pop out because it's a function of x, has to stay in the integral. And then this, which is the arc length formula, right? So what's in red was arc length, right? If you want surface area after you revolve this around the x-axis, then the only change is a 2 pi out here, and you have to multiply by the function itself also. Now that may make you think like, well, you know, that's terrible because now it's even more complicated. But this actually sometimes saves you. Having this out here gives you something like where you can have like a basic u sub, like a u du or something, and it can be nice. All right, so we just apply the formula. Right, that's what we would do. Someone give you a problem, say what's the surface area, apply the formula. So I have an opportunity for you, a take-home quiz. All right, and I'm not going to do a single example of this today. I'll pick up maybe next class I'll do an example. But do you all see there's really not a big change to what we just did a second ago? What I am interested in is this. So this is your quiz. Take home, do next time. If you were to take the sine curve and just look at that first arc of the sine curve, just this first arc right here, and rotate that arc around the x-axis. You would get some weird, almost football-shaped thing, right? I don't want to know its volume, okay? I'm not asking you for the volume, because that would be me asking you to take the whole region and wrap it around, right? That's not what I want. I just want the arc wrapped around, hollow inside. What's the surface area? Okay? So surface area, this thing wrapped. That's my three-dimensional picture of it, right? That's my 3D picture. What's the surface area? Question mark. What are you going to need in order to do this? What are you going to need to do? Take the derivative, square it, right? Plug it in here, put the original function out here, and then start cooking up your methods of integration and see if you can figure out how to integrate it. All right, now as far as homework for the other sections, I forgot to write them down and tell you, what it is. So what I'm going to do real quick is I'm going to bring up my lecture from earlier today, and I'm going to see if I can just get to the homework here at the end. Oh, there it is. Okay. I'll write it down again because it's hard to see. But for 7.4, page 391, problems 7, 9, and 15. And then from 7.5, page 397, problems 5, 7, and 11. So there's really like 3 things you should do, well, 4 things you should be doing tonight or before we come in again. Remember, there's an assignment from 7.2, number 38 and 39, which I didn't really cover, which were the cross sections. 7.4, which is arc length. 7.5, which is surface area, which I have not even given you an example of. And then the quiz on surface area, which will be due next time. We come in on Thursday, and we will talk briefly about 7.6, which is applications. And I'll just tell you ahead of time that the applications section, I always feel bad because I want to spend like 3 weeks in the applications section because there's lots of cool stuff in there. But this is not an applications course. So I have to kind of choose, just sign it. I have to kind of choose, sign-in sheets coming around, what I want to show you, and what I think we can go without. I mean, you technically could go without the whole section, but it's nice to see something, these integrals used for something. So the things that I've chosen are things like calculating work done. So like physics, force times displacement is work, so we can compute how much work is done on an object. And then I'm also going to do center of mass and centroids and moments of inertia and things like that. So some physics things. I'm not going to do hydrostatic pressure, which I like that topic too. But so I'm just letting you know, we're going to do 7.6 briefly, couple of topics, and then we're going to move on to chapter 8. Okay? Any questions while the sign-in sheet's going around?
How far are we from the next test?
The next test,